Okay. All right. So this next video covers sections 5.1, 5.2, and 5.3. So last week we had in terms of what's called antiderivatives. So today we'll get to the real term for this stuff, which is called integrals. So I want to find the area underneath my curve of y equals x squared. So when x is 1, y is 1, when x is 2, y will be 4, and when x is 3, y will be 9. So let's say I want to know what is the area underneath the curve from x equals 0 to x equals 3. Well, I know how to find area of rectangles, so I can say, okay, here's a rectangle from 3 up to 9, and here's my area. So my first guess is that the area is going to be given by 3 times 9, which will be 27. And obviously that is not going to be a very good answer because 27 includes a whole lot of stuff that really is not under my curve, right? So what happens if I try to do this a little better? So let's say now we decide, okay, well let's break this up, and we got a rectangle here, we got a rectangle here, and we got a rectangle there. And let's look at what that would be. Well, this will be 1 by 9 for my first rectangle. This rectangle is 1, the height of 4. And then this is 1 by 1. And so now we're down to 14. Much better than the 27, but it still includes a lot of stuff that is not under my curve. Right? So we can start even getting better than that. Right? So let's say now we decide to break each one of these up into halves. All right, so we're going to split each one of those rectangles in half. And so the area now given would be 0.5 times 0.5 squared plus 0.5 times 1 squared, 0.5 times 1.5 squared plus 0.5 times 2 squared plus 0.5 times 2.5 squared, and then 0.5 times 3 squared. And if I do that, we end up at 11.375. So each time I make my rectangles that I want to add together smaller and smaller and smaller, I'm going better and better in terms of getting the area underneath my curve. So in terms of this last example, my rectangles are now looking like this. Okay. And so you can see that I'm doing better, okay? But I still include a bit of stuff that's really not underneath my curve. Well, I could keep on doing this. I could cut that in half again and again and again. And each time I make my rectangles skinnier and skinnier, I keep on getting a better and better answer, right? So if I make my rectangles in terms of how skinny they are, so we started out with one big rectangle, but we go from 1 to a half, to a quarter, to an eighth, to a 16th, to a 32nd, to a 64th, so on, so on, and so on. And each time I do that, I would get a better and better approximation of the area underneath here. Right? Right. So you get in terms of what this stuff is called, and we get to what are called integrals. The symbol for which is going to be this. Okay? It'll be in terms of some function, whatever it is, and then dx. Right? It is a general way you're going to see this right now. Okay? So for integrals, there are 2 types. We'll mention both today. Today we're going to deal with definite integrals. Next week we'll talk about indefinite integrals. But indefinite integral would be something that looks like this. And a definite integral would be one that looks like this. So the ability you can tell the difference here is that in definite integral, we're going from a starting point to an end point. So really this would be like the question we just looked at with my x squared graph and wanting to know the area from 0 to 3. If I integrate both of these, or find the end of the derivative, we find out that this one would be x cubed over 3 plus c. And this one will actually end up with a value. And we'll save that for a moment until we get to how this works. Okay? And so in indefinite integrals, we end up with basically an equation. So integrating. So let's look at the one we looked at before in terms of my graph, and let's integrate this. So the process is, again, this is one of our basic forms. We said when we integrate this, increase the power by 1 and divide by the same number, and then we're going to evaluate from 0 to 3. So the next step now is to plug in the numbers. And so we get 3 cubed over 3 minus 0 cubed over 3. And we end up here that this number comes out to be 9. So the area is going to be 9, right? And so you can see that in terms of my first bit down here, that this first number is way off from 9. This is better. Okay. This number, when I decided to cut those rectangles in half, was even better. Okay? And I keep on going and make those rectangles smaller and smaller and smaller in terms of their width, and we get a better and better answer until we get to the answer, which we just found out is going to be 9. Right? So let's look at some examples of doing definite integrals. So we got integrate from 1 to 3 to x squared plus 5x minus 2. Really, this dx out here, really what it tells you is what variable we're integrating with respect to. Right? So actually I can integrate with respect to any variable, so we can take derivatives with respect to any variable. So let's integrate. So here we get 2x cubed over 3, 5x squared over 2 minus 2x evaluated from 1 to 3. So our basic rule of integration, we said, was increase the power by 1, divide by the same number. And then the next step here is just to number crunch. So 2 times 3 cubed over 3 plus 5 times 3 squared over 2 minus 2 times 3. All of that minus 2 times 1 cubed over 3, 5 times 1 squared over 2 minus 2 times 1. And if you number crunch that, you end up with 100 over 3. Right. Well, let's look in terms of a trig function. Right. So we're going to integrate 0 to pi sine x. So in that handout you got a few weeks ago, which had the derivatives at the top, it had integrals on the bottom half. And so if you integrate sine, you get negative cosine. And again, for calculus, everything's done in terms of radians. And so here we get the negative cosine of pi minus the minus cosine of 0. Right? So the cosine of pi is minus 1, the cosine of 0 is 1, and this will end up with a value of 2. Right? So in terms of this, then, you get to what's called the fundamental theorem of calculus. And you get in terms of this, right? Which says we can integrate from a to x. And in terms of what we've just been doing, we can integrate, we get f of b minus f of a, is what we've just been doing in terms of getting our definite interval, right? So, let's look at some more definite interval questions. So, we got this from 3 to 6. 1 over x dx. So again, this is on our basic form of stuff, okay? So this one we're actually going to leave it this way, okay? Because what would happen if I decided to do this by the other way, which is say, okay, I move this up top, okay? But then my rule is to add 1 and then divide by the same number, and my variable here goes away. Okay, because after all, x to the 0 is 1. So we don't do that in this case. We're actually going to leave it in this form because this is one of those forms on that sheet I gave you. And if you integrate this, you get the natural log of x evaluated from 3 to 6. And so this will be the natural log of 6 minus the natural log of 3 by properties of logarithms. This becomes the natural log of 6 over 3, and so this will just be the natural log of 2. Okay. All right. A couple more. So we want to do 1 to 3, x times x to the 4th plus 5. So in this case, for this first one, we want to first take care of this and multiply this out. So 1 to 3, x to the 5th plus 5x dx. Right? Now that we got it like that, again, we can integrate. So x to the 6 over 6, 5x squared over 2, evaluated from 1 to 3. So now it's a matter of just plugging in the numbers. So 3 to the 6 over 6, 5 times 3 squared over 2, that part, minus 1 to the 6, plus 5 times 1 squared over 2. And you plug that in, you end up, all said and done, at 424 over 3. What happens when we have radicals? So 0 to 2, cube root of x dx. Well, do the same thing we did when we had derivatives. We're going to change this into an exponent. Okay, so we get that. So again, the rule is to add 1 and then divide by the same number. So this becomes x to the 4/3 over 4/3. And so this will become 3/4 x to the 4/3 evaluated from 0 to 2. After all, 1 divided by 4/3 will be 3/4. And so then the next step is just plug in the numbers. So we get 3/4 times 2 to the 4/3 minus 3/4 times 0 to the 4/3. And that one will come out to be approximately 1.89. And the last one that looks like this, 1 to 4, x cubed plus 1 over x squared plus the 4th root of x plus 5 dx. Well, let's first rewrite this, get everything where we want it to be. So this will be 1 to 4. X cubed is fine. This time we can bring that up because we're not going to get rid of the x. This becomes x to the 1/4 and then 5. Now that we got it written in the right form, the next step is let's integrate. So this will be x to the 4th over 4. X to the -1 over -1. This will be x to the 5/4 over 5/4 plus 5x evaluated from 1 to 4. Right? So let's go through and simplify this a bit. So this is x to the 4th over 4 plus, this will be x to actually it'll be a minus x to the -1. So minus 1 over x plus 4/5 x to the 5/4 plus 5x evaluated from 1 to 4. Right? So the next step then would be to do all the number crunching of this one. Right? So now it's a matter of plugging in all the numbers. So we end up with 4 to the 4th over 4 minus 1 over 4, 4/5 4 to the 5/4 plus 5 times 4 minus 1 to the 4th over 4, 1 over 1, 4/5 1 to the 5/4 and then 5 times 4. And if you do all that, you end up at approximately 83.23. And with that, that will conclude this talk on definite intervals.